Welcome back. This video is the first of two videos on NumPy. NumPy stands for Numerical Python, the foundational library for numerical computing in Python. Nearly every scientific and data analysis tool you'll come across from pandas to scikit-learn is built on top of it. So what does NumPy actually give you? Plain Python already has lists, and lists are fine for holding a handful of values, but they're clumsy for math. If you have two lists of numbers and you want to multiply them together element by element, plain Python makes you write a loop to do it. NumPy's answer is a new data type, the ND array, short for n-dimensional array. It holds a grid of values, all of the same type, and it knows how to do arithmetic across all of them at once. Two properties make it different from a list. Every element shares a single type, and the size is fixed once the array is created. These constraints are exactly what let NumPy store the data compactly and hand the arithmetic off to fast, precompiled code underneath instead of a slow Python loop. In this first part, we'll cover the groundwork: importing NumPy, creating arrays and letting NumPy generate arrays for you, checking their shape, pulling values out by indexing and slicing, and transposing. In part 2, we'll start putting these arrays to work with a range of operations. So let's start by importing the NumPy library. To do that, I'm just going to type import NumPy as np. Now this is a slightly different import from what we've seen. We've got import NumPy, which we've seen before, but then we've imported it as np. This is called an alias. It means bring in the NumPy library, but let me refer to it as np for short. From here on, every time we want something from NumPy, we write np.something rather than numpy.something. You could pick any name you like, but np is the conventional alias. You'll see it in documentation, in textbooks, in every example online. So if you use np, your code will look familiar to anybody reading it. Let's make our first array. NP array takes a plain Python list, that's the part in the square brackets, and turns it into a NumPy array. These arrays are one-dimensional, a single sequence of 3 numbers with no notion of a row or column yet. That distinction only shows up once you have 2 dimensions. So let's see how we can make a 2-dimensional one. So look carefully at the square brackets here. We've got an outer pair, and inside it 2 more pairs. Each one is a row. So this is a 2 by 2 matrix. The first row has 1 and 2, and the second row has 3 and 4. Splitting it over 2 lines like this isn't required, but lining the rows up makes the structure much easier to see. Python doesn't mind the line break because we're still inside the brackets. So let's print this out. Quick note on how we're printing here, since this is the first time we're using it. The F right before the opening quote makes this an F string. Inside it, anything you put in curly braces gets evaluated and its value dropped straight into the text. So this gets replaced with the contents of A, and that's what you see in the console. The same goes with M. It's the cleanest way to mix text and values in print, and we'll be using it all series. There's more you can do with F strings, but we'll save the details for a future video. For now, just read the curly braces as put this value here. Notice how NumPy prints these. The 1D array comes out on a single line, and the 2D one is laid out over multiple lines, 1 per row, so you can actually see the shape of the array. And the \n that we're putting in our print statement is what dropped the matrix into its own line below M. And notice one more thing. There are no commas between the numbers when NumPy prints an array. That's how you can tell at a glance you're looking at a NumPy array rather than a plain Python list. So now we're going to let NumPy build arrays for us. So typing out every value gets old fast. So two functions that will save you from that are arange and linspace. So I'm going to type them out and then we'll talk a bit about it. So arange builds an array by stepping. Start at 0, stop before 10, step by 2. And I do mean before 10, since 10 is not included. The stop value isn't included. You get 8 as the last element and not 10. And linspace is the one that I usually reach for more often. It takes a start, a stop, and how many points you want, and it spaces them evenly for you. Here, start at 0, stop at 1, and give me 5 points. And unlike arange, linspace does include the endpoint. So let's print this and see what that looks like. And there you can see the difference. Arange gives us 0, 2, 4, 6, 8, no 10 because 10 is the stop value. And linspace gave us 5 evenly spaced steps, and it did include 1 at the end. So the rule of thumb, if you know the step size you want, use arange. If you know how many points you want, use linspace. The next topic is the shape of an array, because shape is what determines whether an operation will work at all. So let's print the shape of these two arrays that we're working with. A.shape gives us 3, and this is a tuple, Python's way of holding a fixed group of values. This one has a single value in it, 3, meaning 3 elements along one dimension. The trailing comma looks strange, but it's required. Without it, 3 would just be the number 3 in parentheses. The comma is what makes it a tuple. M.shape gives you 2, 2. 2 values this time, so 2 dimensions, 2 rows and 2 columns. The number of values in the tuple tells you how many dimensions the array has. 1 for A, 2 for M. A key point is how we're getting the shape of an array. There are no parentheses after shape. Shape is an attribute or a property of an array and not a method or function that you call. Compare that to np.array up here, where the parentheses are you calling something and handing it a value. With shape, you're just reading a value off of the array, so there's nothing to call and no parentheses. When something goes wrong in NumPy, printing the shape is almost always the fastest way to find out why. Once you've got an array, you'll want to pull individual values out of it. That's called indexing. So let's print some values and talk about what we're looking at. A couple of things here. We're using square brackets for indexing, and the number inside it is the position that we want. And notice we start counting at 0 and not 1. A0 is the first element and A square bracket 1 is the second. The 0-based counting is standard across Python, and it takes a little getting used to. You can also count from the other side using negative numbers. A of -1 is the last element, A of -2 would be the second to last, and so on. Handy when you want the end of an array without knowing how long it is. For a 2D array, you give it 2 numbers, the row first and then the column. M0, 0 is the top left value, row 0, column 0, and M1, 0 is row 1, column 0, just like in math. So it's always row first and then column. Indexing pulls out one value at a time. Often you want a range of values instead, and that's called slicing. And it uses the same square brackets with a colon inside. Let's use the counts array that we generated with arange and see how we can slice some values. The colon is key. Counts 1:4 means from index 1 up to but not including index 4. So it gives us the values at position 1, 2, and 3. That's the same up to but not including rule we saw with arange's stop value. The number after the colon is where it stops, and that endpoint isn't included. You can leave either side of the colon blank and it fills the obvious default. Leave off the start and it begins from the very first element, so 0, 2, and 4. Leave off the end and then it runs all the way to the last, which is 4, 6, and 8. And negative numbers work here too, the same way they did with indexing. So count -2 colon means from the second to last element to the end. A quick way to grab the last few values of an array. Slicing works the same way on any array, and it's how you pull out the piece of data set that you care about. One operation you'll reach for often, especially with matrices, is the transpose function. It flips an array over its diagonal, turning rows into columns and columns into rows. So let's use the transpose function. There it is. The top row of M1 and 2 now becomes the first column on transposed, which is M transpose. You can also use a function form that does exactly the same thing. Use np.transpose and then give it the variable M. And then we can print it out and it gives you the same value for both the cases. So you can just use either. .t is shorter, so it's what you'll usually see. Use whichever reads better to you. One thing I want to note is transposing a 1D array leaves it unchanged since there are no rows and columns to swap yet. Transpose only really means something once you're in 2 dimensions, which ties back to the point earlier about a 1D array having no notion of a row or a column. So that's the groundwork. We brought NumPy in under its standard alias np. We created arrays by hand, 1-dimensional and 2-dimensional, and had NumPy build some for us with arange and linspace. We checked their shape, pulled values out with indexing, and flipped them around with transpose. In part 2, we'll start putting these arrays to work and cover the main operations you'll use on them.